And I connect every point to points which are close to it up to 12C. Okay, 12 is just a constant that. An n, yes, sorry. So in our observation, there exists a number n which depends only on this lambda, such that the degree of this graph is at most n. Okay, this is where we use the doubling condition, because what does it mean that a point has many neighbors?
Do you care how the graph is finite or infinite?
Doesn't matter.
It doesn't matter. So you may assume the x is bounded.
Yeah, all of these things don't matter here.
Yeah.
Okay. So you have what does it mean? So here's a point in my net. This is a point in the net, and let's look at the ball of radius 12C. So what does it mean that it has m neighbors? Okay. Well, it means that in this ball of radius 12C there are m other points from the net, but these are points from the net, so they're all at least C apart. So around each of them we can draw a little ball of radius C over 2, and these balls are going to disjoint. Right? Therefore, if I want to cover this ball of radius 12C by balls of radius, I don't know, C over 4, I need at least n many. Is such ball, because any such ball can intersect only one of these. So a ball of radius C over 4 in the big space cannot intersect two of these, cannot contain more than one point of this net. Okay, which is a triangle inequality. So I need at least n balls to cover of radius C over 4 to cover this ball of radius 12C, and that's the doubling condition. Dividing, if you're doubling, you're also quadrupling, so you can cover every ball radius by half the radius and every of these balls by balls a quarter of the radius.
You don't need this disjoint ball.
They're just far away. Yeah.
Any ball of size.
Yeah, they're just far away. These points are far away from each other. That's all I mean. Okay, so the degree is bounded. Okay, but and bounded by some function of lambda. When you care about bounds, you do it carefully. Okay.
But it's a polynomial, even this proof.
Yeah,
There's
it's
some
a
power
polynomial.
of lambda.
Yeah. Okay, so the degree is bounded, and so where were we? So the way I'm going to use it is just I'm going to color it. So we can color n with this graph by m colors. So there's a function chi from the numbers 1 to m to n, such that if dxy is at most 12c, then they get
The coloring goes
sorry. Okay, so that's the way we're going to use it. And now what we're going to do is for every color, what the slot does is for every color he chooses a coordinate. So now let E1 up to EM be the coordinate basis of Rn, and define a function phi from all of my space x into Rn by phi of x is the sum over all points z in the net of g sub z of x e chi of z, where gz of x is 1 at the center. So if I draw a ball of radius 2c, and I look at the function which is 1 here, and decreases linearly to 0. That's it. Okay, so g sub z is a Lipschitz function because I started from in 2c, I went from 1 to 0. This is going to be a Lipschitz function, Lipschitz 1 over 2c. Lipschitz function 1 over 2c. Okay, so let's think for a moment, what does this phi do to us? So first observation, in the sum, which defines phi, what? Well, it just in the sum star, there are at most, I don't know, C0 depending only on lambda points for every x. And what's the reason for this? So a priori I wrote an infinite sum where if it defines it unboundedly many points, but actually this is boundedly many points because the only points x which get a non-zero contribution, g sub z, are points which are disease which are distance from x at most twice c. But this is a net, so this is a c net in a doubling, a c net in a doubling space. So again, the same argument. We show this is just boundedly many points. Okay, so this is all. Everything is fine, but this also implies that I guess the L2 norm of phi of z, because there are all these functions g sub z are bounded by 1, so and they're at most c0 coordinates, so the number of points here is at most root of c0. Okay? For every x in x. This is a bounded function. We'll use this like that. We'll write this phi x minus phi y is at most 2 root of c0, which obviously follows from this with a triangle inequality. So this is one of the properties of phi. And then there is another property. So second observation. Second observation is that phi x minus phi y is also, so let's look up here. There are at most these C0 sums in the sum. Each of these functions, g sub z, is Lipschitz with constant 1 over 2c. Right? Because they decay linearly. So you have here at most this root c0, the Lipschitz constant 1 over 2c. This is just for each coordinate times the distance from x to 1. That's true. Okay? That's clear? Yeah.
Shouldn't you look for a lower bound on x minus dy?
Of course. Third observation. Yeah. I'm not done. But I need this. I should look also for upper bounds. So the third observation is yeah. Yeah. So if what happens if I take 2 points in my metric space whose distance is at least, let's say, 4c and at most 8c. Okay, so roughly the distance is in this range. Then the observation is then the vectors phi x and phi y in Rm have disjoint support. Why? So the support corresponds to some sort of this is where I use the color. So here's x. Okay. If x has a non-zero coordinate at some point, this is because here one of the summons contributed something, which means the distance from x to some z1 is at most 2c. Okay? And the same for y. If the same coordinate contributed something to y, then this is distance at most 2c, and this distance here is at most, what did I say? This 8c. I think that's why I wrote 12. Then this in particular means that the distance from z1 to z2, these are points in the net, is at most 12c. Therefore, they got different colors. But if they got different colors, then they're sitting in completely different coordinates here. Okay? That's how the coloring means. So it's a crucial. Okay, so we're encoding this in this geometric information using coordinates. So okay, is that clear? So they have this joint support.
So you didn't use at least false the anyone?
I didn't use it, but that's all I'm going to need for the lower one. No, I don't try.
The same point.
They were the same point.
Use the boards are.
No, not in the same as.
Oh yeah, and I want to say that z1 is not z2. Yeah. Yeah. Okay, so is that clear? Should I say more? So they have this joint support. So then I get a lower bound. So quadruple star phi x minus phi y. What do I know about it? Well, so this is going to be quadruple star. That equals, they're orthogonal. So root of phi x squared plus phi y squared. And so now let's look at the sum up here, and I say, well, for every x, there exists one coordinate, one of these z's in n. So every fixed x in the metric space is close up to some z up to c. Right? This was it's written somewhere. I erased it, but this was a c-net. So there is one coordinate in which g sub z is at least a half. Okay, so when I do this, well, clearly this is at least some universal constant. Okay, so now let's copy this information, and we see that this is all we need. Okay, so
when this is also half.
not at least it's at least 1 over root 2 if you, right? Yeah, doesn't matter. Okay, so that's all we need from this. So let's summarize. Exactly. So this is where this multi-scale analysis comes up, the terminology. Now we're going to, let's see, run over all the possible scales of distances. So let's rewrite these conditions that we got, but for so now we'll take C to be 1 over 2j plus 3. That's because of the 8 over there.
CCO was independent.
Z only depending on lambda. Okay? Okay, the ratio between the 12C and the C over 2 or whatever.
Whenever you change C, then say embedding changes, right? So
Yeah. Okay, so for this C, then what do we have? We construct for each j. So for each j, we constructed a function phi j from x into Rm, but it's the same m at each step. Okay, so it's such that, so now let me write down all of these things together. One is so for phi j, if the distance from x to y, you could localize it. I knew that it's between, let's say, 1 over 2 to the j plus 1 and 1 over 2 to the j, then phi j of x minus phi j of y is at least some constant. So there's going to be constants a and b, and I guess what else? A and b, which only depend on lambda, and M only depends on lambda. Everything just depends on lambda, okay? So this is this one constant, that's this lower bound. Well, actually it's 1 over root 2, right? Okay, but it's a constant. So in this scale, I know that the points are mapped far apart, and for every 2 points, x and y in x, phi j of x minus phi j of y is less than some b, which is really depending, times the better of the two. Well, it's bounded by a constant, but we get this. Okay, so just the first term is just saying that phi is bounded, less than this 2c0, and the second term, 1 over c was like 2 to the j. I swallow away all the constants in this b. Okay, so I mean, the better bound, the Lipschitz condition kicks in when dxy is below this critical 1 over 2 to the j range. Okay? Okay.
So for very close points, you get bound, and for points that are not too far apart and not too close, you get.
Actually, the opposite. For very close points, I will use the Lipschitz condition now. For points which are far apart, I will use the a priori L infinity bound. And I'm going to use the fact that I know that for every fixed scale, there is one of these phi j's does a good job for me. Okay, so let me glue all of this together, and then we'll finish a Swad's proof. So all of these ideas are very important ideas that we use a lot. Okay, those of you, I mean, there was this one disturbing issue in the Swad's theorem, which was we raise the metric to the power 1 minus epsilon. At some point, this has to come in, and this is where it's going to come in. We're going to try to sum all of these up in the right way, but we'll have to make something converge, and that's where we're going to use this epsilon condition. And you will see that we really need not epsilon, but logarithmic corrections.
Sometimes the log come because there are log many scales, or
Which log?
the
There
logarithmic.
are infinitely many scales. You don't know what.
You have no idea. I mean, yeah, yeah. You will see. Okay. So now let D. Okay. So.
Just to make it clear, you have this set of embeddings, and each one is good for different subsets of the pairs.
Yes. Yes.
But it's not too bad for the other.
Yeah. And this basic philosophy is this approach of a Swad is what we're doing all the time today. So this is really the first, the grandfather theorem of this theory. We'll see the second, the grandmother, in a second. I hope Wergen isn't here. But, okay. Yeah, it's recorded. Sorry. Okay. So let me just write what the formula is. So we'll take D is going to be some function only of lambda and epsilon. So now I'm fixing epsilon. I'll tell you in a second what D is. Okay, so it's going to be an integer, and we'll let U1 up to U2D, this is just for convenience, be the standard basis.
What do you call it? D was your
K.
distance.
It's also going to be dimension, but I mean, it's true, in all of this theory, whenever people write R to the D, there is a chance that somebody will be confused that we're raising the R to the power of the metric. Okay, so if you think that that's what I'm doing, ask. Okay, so I prefer it because I'm otherwise gonna have a different notation than in my notes. Is that okay? But that's how D is going. Is that okay?
You have to say that you are
Yeah.
your own variable.
Yeah. So I mean, yeah. So U1 up to U2D is the standard basis of RD. Okay? And I'm gonna do the convention that Okay, and I'm gonna do the I'm gonna make them continue in a periodic way. U2d plus j equals U2d. So I will have coordinates for every integer j. Okay. Switch color. 2d plus j. To uj, and I will switch to blue now. And now my embedding is going to be, the final embedding is phi of x is the sum over all scales j and z, so from minus infinity to infinity, and the scale is 1 to 2 to the j, but I'll get 1 minus epsilon here, and what I'll do is I'll take phi j of x, and I'll tensorize it with uj. Okay? And let's see what happened. So first of all, this is all an embedding into some finite dimensional space. M times 2D. Okay? So let's, so here is the really baby version of multi-scale analysis of this function. So we take x and y in x, and let L be the scale which we care for this specific pair. So L be such that the distance from x to y is in the interval 1 over 2 to the L plus 1 over 2 to the L. Okay? We choose this L, and the upper bound is very simple. So what can I say about phi x minus phi y? Well, I'll just use a triangle inequality, but I'll break it into two sums. The sum j is at least L.
Assaf, you assume that the maximum distance is 1?
No.
Okay, so the dxy could actually lie...
It's the sum is over integers, negative and positive.
xy, dxy, you assume that it's always less...
L can be negative.
L could be negative.
The sum is over all, the scales are run over all the integers, big and small, okay? Okay? Yeah, so let's just write it. The sum j is at most L, 1 over 2 to the j, 1 minus epsilon, phi jx minus phi jy, plus the sum j less than L of the same thing. And I want to use condition 2 above, so I better use it in a smart way. For large j, I'm going to use the a priori bound is 1, and for small j, I will use the better Lipschitz bound. So we get sum j is at least L, and here we have 1 over 2 to the j, y minus epsilon, there is a b. That's that. Plus sum j less than L, and now we have 1 over 2 j, 1 minus epsilon, and now we have again this b, and now 2 to the j times the distance from x to y. Okay, I'm using number 1 above. So this thing behaves like just the Lth term. So now when I do twiddle, I'll include the b's. Twiddles are allowed to be functions of epsilon and lambda, okay? So this behaves like a 1 over 2 to the L, 1 minus epsilon. This is the first term. It's a geometric series. Plus the second term, so what's written here? We have the distance from x to y, sum j less than L, 2 to the j cancels, and we have 2 to the j epsilon. So now we go to minus infinity, so what again, the Lth term is what determines everything. But 2 to the L was roughly the distance. So we have the distance from x to y times to the power 1 minus epsilon. That's the first term. This is the distance
from x to y to the power minus epsilon, so we also have just 2 to the L is this distance, and that's exactly what I needed. Okay, so that's the Lipschitz condition, and we needed this epsilon to make this term converge. Okay?
What is the choice of D and where did
Now in the lower bound. Now in the lower bound. That was just a Lipschitz condition. That was just, the upper bound I don't need to choose the D. Okay, now I need to prove that it's by Lipschitz. Okay? So by Lipschitz in this metric D to the power 1 minus epsilon. Okay. So I'll erase this because I want to keep the two conditions. So now, I wanna, so it's again, as before, the distance from x to y is in the interval 1 over 2 to the L plus 1 over 2 to the L. And phi x minus phi y is this huge sum over here. So what I'm gonna do is I'm gonna use a triangle inequality this way. I'm gonna keep inside the sum all those j's which are between minus, which are roughly L. So j minus L is at most D, okay? Where is it? 1 over. And I'm going to just throw away everything outside this crucial interval, okay? So I have a sum j, I do it, j is bigger, so let's do it. Bigger than D plus L, 1 over 2 to the j, 1 minus epsilon. It's phi jx. Minus the small ones, less than minus D plus C. Okay, so I'm just using the triangle inequality this way. And what does Aswad tell us? It says these we're going to bound exactly the same way, and this is where D large enough will come up. Okay, but now these objects here are orthogonal. So because the user, the periodicity is of order 2D, the j's which are up to plus minus D away from this crucial scale L, they are orthogonal directions. So, so this is at least, in this term I'll just take the Lth direction, I'll throw away everything else. So 1 over 2 to the L, 1 minus epsilon, but then, I forgot here phi x minus phi y. Okay, but at this crucial dimension scale, number 1 kicks in. We know that I get at least a constant. So this is the distance with the 1 minus epsilon, and the rest is going to be negligible, because when you do the same sort of computation, so minus you get here b sum j greater than D plus L 1 over 2 to the j 1 minus epsilon. I'll use the a priori bound, and here I'll use again the distortion, the Lipschitz bound. Times 2 to the j times the distance from x to y. Minus D plus L. Okay? So again, I'm going to forget about constants. So here I have the distance from x to y to the 1 minus epsilon, minus, what do I have here? Again, as before, what's critical here is so we have the distance between x and y. Here's an example where the D was unfortunate, but so 1 over 2 to the L, 1 minus epsilon, 2 to the D plus L. You'll have to forgive me. Minus, and here we have, again, the distance from x to y. And now it's going to be 2 to the epsilon minus D plus L, as before. Okay? And you see that the L term is this d to the 1 minus epsilon, and it gets hit in each of these by 1 over 2 to the d. Okay? Or 2 to the d epsilon. So if d is large enough, but large enough just as a function of epsilon, then all of these are negligible with respect to that. Not as a function of x or y or anything. And that's the end of a SWADS.
So dxy was about 1 over 2 to the a.
Yeah. So this thing here is something like 1 over 2 to the d 1 minus epsilon dxy to the 1 minus epsilon, right? Because the L term is exactly the distance from x to y. And here, the 2 to the minus 2 to the epsilon L is going to give you, again, dxy to the 1 minus epsilon. And you're going to lose 2 to the minus epsilon d. So if d is bigger just as a function of epsilon, then all of the coefficients of dxy to the 1 minus epsilon are just negligible with respect to the 1 here. Okay? And you can get all of these to concrete bounds if you want. That's not a... Okay, so that's a very important, very classical, probably the first really real embedding theorem. Yeah.
The follow from this is if you can embed locally kind of a metric space. If you can only embed this some part of the metric, some scale of the metric space, then you could embed the entire metric space.
That's what all we proved. We proved that 1 and 2 implies the embedding result.
Yeah, but for any
We didn't use a doubling condition after we had 1 over 2. This is just, right?
No, but there's something like that more generally true, right? Your gluing theorem.
yeah, it's like a general theorem.
Yeah, this is the gluing theorem. They're just so the better ones just get better bounds as a function of all the parameters here. Okay? If you care about the bounds, how everything depends on everything, then you work much harder, and that's important for certain applications. But these are general. This is the first gluing theorem of this type. Yeah.
Would this be a good time to take a 5
Oh,
minute break?
yeah, sure. And then we'll. Yeah. So Bourgain's embedding theorem says that if XD is a metric space, has n points, then it's Euclidean distortion. C2 means embedding into Hilbert space. So is at most, I don't know, we'll get 16, I guess. Let's write 100 log n. We'll get a small constant right now. So, okay? So it's at most a constant times log n. And so this is optimal. This cannot be improved. So Bourgain showed that up to log logs showed this is at least log n over log n. So there are spaces of this form, and Lineal, London, and Rabinovich got rid of the log. So this is optimal. I'll say a few words about these lower bounds if we have time, but I really want to prove Bourgain's theorem. So here is the proof. So X has endpoints. So what we're going to be doing now, we were discussing this also in the break, we're going to do again something which is a multi-scale construction, but the multi-scale will be at the level of densities. We're going to look at how many points are at balls of certain radii, and we're going to scale those according to power of 2. So this is a multi-scale in a different range, and then we're going to say a few words about what happened, what happens when you try to unite these two approaches. Okay. But, okay, so for every subset A, let's define, and for every number J, so from now on I'll denote K to be 1 plus log to the base 2 of n, round down, I guess. And so this is k from now on, and if for every j which is in 0 up to k, I'll define in a subset A of x, I'll define pi sub j of A to be a, so I'll start by giving a formula and then we'll see what it is, what it means. So this is pi sub j of A, and if we'll define alpha A to be the average, we'll see in a moment what this means and it will all make sense. But now, so all of Bourgain's theorem is the following statement. Define a function f from x into R 2 to the x, so 2 to the x, all the possible subsets of x, by f at the point x with coordinate A is just sum over all the subsets of x, root of alpha A, the distance from x to A. Okay, so, sorry, no sum. Okay, that's it. Okay, so there's this number, we take the root of this number, we take a function which has coordinate for every subset, this is the coordinate, and the claim is that this works. Okay, so, but of course we'll see what it means. Of course. Okay, but the claim is this works. So this f has distortion. It's very concrete. So it's just a formula, okay? And actually that's the way it's written in Bourgain's paper. So there's a formula and then there's computation. But let's see what it means, where it came from.
Can you also do it with the dimension, so the 2 to the n?
Of-
n? Yeah.
So log n even, we'll see when there is dimension reduction. This is right now I'm just giving you a clean formula. The dimension will be log n in the end, but you don't, if you just care about polynomial, about an embedding, this is, as I said, any embedding into L2 can be computed efficiently. This is a semi-definite program, so we don't need that right now. Okay, but all of this can be done in low dimension with few ways, and we'll see from the proof. It will be obvious, but I will explain it. Okay? I will explain it.
Yeah, you could have.
Yeah, but I didn't say it yet. This is okay. You know, but we'll get to it. But you could also just analyze this proof directly and see that you don't need many. You don't need some other, like Johnson and Strauss. You can analyze the proof directly and see that you don't need many coordinates. Okay, so why does this work? So of course we need to say what pi j is. So here's x. Here is my metric space x. And now we let aj be a random subset such that every x in x is in aj with probability 2 to the minus j, independently of the others. So for everyone, you flip a coin with bias 2 to the j, and that's aj. This is this random subset. So pi j of a is just the probability that aj is a. Okay, that's a. So this is what this pi j is. And now right away you see that f is obviously Lipschitz, because fx minus fy squared is just the sum over all a's, alpha sub a, the distance from x to a, minus the distance from y to a, squared just by the formula, which is this 1 over k, sum j goes from 1. So I don't need it. I'll just say that's at most. Distance from a set is a Lipschitz function, so that's sum over a alpha a times the distance from x to y squared. But the sum over all a alpha a is 1 because alpha a is it's an average of k probability distributions. Okay, so
By the way, your alphas and these are dangerously close to each other.
the alphas n,
And these.
yeah, but that's less of a crime than what I did before, right? So, no, actually, at least now I think that it's a different variable. But so this is one. Okay, so we get that f is Lipschitz. So the whole point is the lower bound. That's all we need to prove, and maybe I'll keep it. So everything hides in the lower bound. So everything is in the lower bound, so the claim is that for every x and y, the distance from fx to fy is at least a constant over log n, the distance from x to y. Okay? So that's really where everything is. So what you do is you, for every j in 0 up to k, so fix x and y. So now we're fixing x and y. Okay, from now on, so for every j, let rj of xy be the smallest r such that the number of points in the ball around x of radius r is at least 2 to the j, and the number of points in the ball around y of radius r is at least 2 to the j. So we're looking what is the r such that, here's the picture, I'll keep it up there. Well, so here's x, here's x. So I want to find the smallest r such that in here I have at least 2 to the j points, and also for y simultaneously. Could be a bigger ball. So in some sense, we're measuring in this multi-scale way the local densities around x and y. Okay? Okay, and now technicality, but I have no choice but to do it. We will need a truncated version. You will see y in a moment, but we'll define r twiddle j of xy to be the minimum of rj of xy and the distance from x to y over 4, that's over q. So I just don't want the balls to be too big. Okay, that's the truncated version. Okay. So the key claim, which isn't hard, is that for every j, I look at the probability that the distance from x to a sub j, remember a sub j was this random subset where each point was taken with probability 2 to the minus j. So I measure the distance from x to this point and the distance from y to this point, and I say that these numbers are different by how much? By at least rj, the increment of rj twiddle. So this probability is at least a universal constant. We'll get, I'm sure about this. So, okay?
Can you insert a corner for alpha a and you write it down so that you never use it?
So pi j of a is this probability that aj equals a. So this is 1 over 2 to the j a times 1 minus. Okay, and alpha a is 1 over k sum pi j of a. Okay? The average of these. So this is the claim. Assume the claim for the moment. I'll prove it to you. Let's see how we finish assuming the claim. So So I get this increment which depends on x and y, but on the growth rate of the balls around x and y. So assuming the claim, just for a moment, here is how we finish Bourgain's theorem. We just say, what is fx minus fy? Euclidean norm. So this is the sum over all subsets of x, alpha sub a, the distance from x to a, and the distance from y to a, right? That was the definition of f. And so now we can just use the definition. So it's 1 over k, sum j goes from 0 to k, pi j of a, sum over a, pi j of a, of the same thing. But what's written here is the expectation with respect to this aj of this random variable, the distance from x to aj minus the distance from y to aj squared, because pi ja was the probability that a set equals aj. Okay, so, and by the claim, this expectation is at least a universal constant. And this expectation is at least this increment. Okay, so by the claim, this is at least some universal constant. I have this 1 over k. There is a universal constant. Sum j goes from 0 to k. And now we have here rj twiddle of xy minus rj minus 1 twiddle of xy squared. And now I do Cauchy-Schwarz, and I get constant over k squared. Sum j goes from 0 to k. Now I'll have a telescoping sum, rj twiddle xy minus rj minus 1 twiddle xy. All of this squared. But the sum, r0 is 0, because I want at least 1 point, and x is in the ball. And the last r is the distance from x to y over 4, because eventually I get the entire space. So all of this sum is of the order distance from x to y squared. So this is at least some constant, distance from x to y squared, and k is of order log n, so log n squared. And this was the lower bound for the distance squared, so when I get a root, I get what I claimed. So everything is in the key claim. Okay, so we don't need these formulas anymore. Do you want me to keep them? I'll keep them here anyway. I'll keep. You know what? Can I erase what I just did? Yeah. I'll just erase.
I'm still trying to understand this. How comes that all sizes matter, right? Because you are averaging over all j's, right?
Yeah.
So all sizes.
Because for size j, look at what the claim. I just erased it. What is the claim saying? I'm not claiming to get a lower bound which is independent of x and y or independent of j. I get something which the lower bound which I get with high probability is a function of x and y and j. Okay, I mean, in the end, they all sum up to what I need, but I don't know how much I'm getting for every fixed j, a priori.
Yeah, but
That's what.
If they are very close to each other, then you want some say aj is very big.
It's not really about being close, right? It's the question is if there are many, many points near them. That's what you're really looking at, right? So,
Does it make sense that like you will need all scales?
yeah, let's see the proof, and then let's see why there is a lower bound. And okay, so proof of the claim. So this is what I need to prove. So by the definition, I guess, of Rj, yeah. So by definition of Rj, okay. So this is an annoying issue with the truncation, but you will see why we need it. So nothing to prove if these two numbers are the same, right? So let's assume that actually Rj minus 1 is strictly less. So without loss of generality, so that's the case that, so we assume that rj minus 1 is rj minus 1 is strictly less than rj because they're decreasing, in which case this is the same as rj minus 1 without the twiddle, because there was just truncating. And then, what is the definition of rj? So by the definition, either I look at the ball around x of radius r, j, x, y, the open ball. So it's the same inequality, but with a strict inequality in the definition of the ball. So this is, when I write open ball of z, t, I mean all the points w such that the distance from w to z is strictly less than t. Otherwise, I was doing. So this open ball has at most 2 to the j points, or the open ball around y of this has at most 2 to the j points. That's a definition. Otherwise, I could have taken a smaller radius. Okay? So without loss of generality, let's assume this is by symmetry. This is happening around x. And now, so what will be very happy if the following happens. So the good event, is that AJ has a point in the ball around y of radius rj minus 1 twiddle. So this is not empty, but AJ is disjoint from the ball around x of radius rj. Right? Because I think the other way, it is equal, yeah. Because what's happening here, because in that case, so if this is, so this is x, this is this ball of radius rj, and this is y, and this is the ball of radius rj minus 1. So AJ has a point here, does not have a point here. So AJ is completely outside this. So the distance from x to AJ is at least rj. But it has some point here, so the distance from x to y is at most rj minus 1. So this is exactly when the difference of the distances is exactly what we wanted. And now the whole point is that the balls, these two balls are disjoint. So that's the reason for the truncation. So because this rj twiddle xy is at most the distance from x to y over 4, these events are disjoint. These events are independent. So the probability that AJ, what's written here, intersects y. Yeah, that's what I always do. Yeah, 3 probably. If you do less or equal, then 2 is not enough. 2 is the okay. Okay. Equals empty set, just equals. So now I don't need any of this. So I want to have no point from here. So this is 1 minus 1 minus 1 over 2 to the j to the number of points in the ball. Times 1 minus 1 over 2 to the j to the, where is it minus 1 here? This is minus 1. And now the number of points around x with rj. Okay. This has many points, right? How many? At least 2 to the j minus 1, right? Because the twiddle equals the same thing, where we're assuming that. Okay, so we can erase the twiddle here. And this is at least 2 to the j minus 1. And the twiddle is with most rj, so this number here has less than 2 to the j points. So this is all at least 1 minus over 2 to the j, 2 to the j minus 1, times 1 minus 1 over 2 to the j, 2 to the j, and this is a constant. I think I checked, okay? So that's the end of the proof. Is that clear? So what's happening here is some sort of again, this chopping things up into scales, but the scales are the density range, the rate at which balls grow around points. So I'll just quote that there is a way to glue these to combine these two approaches. And that is important for applications that come later, which I just won't have time to mention. But there is a method called measure descent.
But just here we can see that it would suffice to sample about log n balls of every radius.
Yeah. So for every point x and for every k for every j between 1 to log a, choose log n. Random subsets with, yeah. For every x, but there are log n of them, so that's log n squared. Yeah, this gives dimension log n squared. Yeah, yeah. So this would give log n dimension log n squared, and actually for this you get stuck with log n squared. You have to do something else to get log n. But
so what did you say? So what is the choice of the sets?
so what you can so here for every x in the set, and for every number j between 1 up to log n, choose log n subsets, independent subsets according of this form AJ. Okay?
Choose 100 log n.
Yeah, 100 log n.
Okay.
And so this is for every j, you choose log n of this, so you get log n squared. Okay, that's it.
And is there any way to reduce log n without Johnson and Schwartz?
What does it, to do it without? What do you mean by doing it without?
So how do you get from log squared to log n? Is there any other way to do it?
Well, so, yeah, so there is a paper of Bartal, Neyman, and another name which I forgot, which does this for all LPs. So the point is, there's an analogs of these which.
This proof is more or less independent of A2, right?
Yeah, so
Because you get it anyway.
the only dependence on L2 is that I chose root of alpha A, and you need a different power. But so you get dimension log n squared in any LP space. In L2, so there is a proof, but what you see when you look, so there is a proof which works, which gives dimension log n in any LP space. That's a non-trivial fact because we don't have dimension reduction in other spaces. But when you look what it does in L2, then it's just a random projection. It's summing them up with random signs in the right way. So I mean, so in L2 it reduces to things that you've seen before, but there is an analysis which is non-trivial in the LPs.
That's these people, Bartla,
Yeah, Neyman and the third one which I'm forgetting, which I'm sorry, but okay. But so it is a non-trivial thing, but it becomes non-trivial when you go to L4, let's say. In L2 it will summing up these coordinates with random signs. Okay, so. So there is a way. It really is combining the local growth approach and the multi-scale metric approach And it's subtle. I mean, there are many, many versions of it, but like one of the corollaries would be that if x is finite and doubling with constant lambda, so I want to somehow combine these two situations, then I can prove that C2x, so this is due to Krauthammer, Lee, Mendel, and myself, then you get some constant, and then you get this log of the doubling constant times log n. So this implies Bourgain, the geometric mean of the two. This implies Bourgain because every endpoint metric space is doubling with constant n. That's an absolute triviality because cover every point by all the points in this, every ball by all the points in the space. And it's optimal also when lambda is a constant. So Laxo proved that this is optimal. Optimal when lambda is a constant. And Bourgain proved, or Linen-Rabinovich proved, that it's optimal when lambda is the worst possible. So you believe that this is an optimal interpolation, but it's actually, we do not know that this is an optimal interpolation between the two bounds. So there is, what is the way to interpolate between constant doubling, doubling constant and the worst possible? It's not obvious. I mean, we really don't know. Okay, but okay, so.
Examples for the big constant are from expanders, right?
For the log n, you mean?
For the log n.
Yeah.
For constant, for lambda equals constant.
It's it's precisely, so there are many examples, but the first one is due to Laxo, which is the first one which okay, I'll explain in a second. So what you do is you do some iterated construction of this form. I'll define a sequence of graphs. Okay, so I'll start with an edge, and now I'll take the middle of this edge and replace it by a quadrilateral. And I will iterate this for every possible edge. So now I take the middle of this edge, and you iterate this, okay? So you need to prove two things. This is doubling. These objects are doubling with constant independent of the number of vertices, 10. So 6, I think. The doubling constant happens to be exactly 6 here. We need something, well, not necessarily, so there are other examples showing that this is optimal. So there are other constructions of Laxo, which I can explain to you later, which also give that it's a constant doubling constant, and root log n distortion. And it turns out, this has never been published, but this is true, that the original example of Pansu, which is this discretized version of the Heisenberg group, also shows that this gives really the optimal root log n here. Okay, so there are many candidates for the beginning of the interpolation. In the end, it's always expanders. I'm not sure that this is the thing you want to start out with, but maybe. Okay.
This embeds in a constant Euclidean dimension, right?
Yes. If you take Snowflake, yeah. But so this in particular will, because I told you that Laxo told you that you get at least root log n here. In particular, this theorem of a SWAD, you need this epsilon in it. But this is a much later example than the original Pansu example. This is a decade afterwards.
Does this embed into L1?
Yes. Okay, so I will I have 10 minutes, and I will have to skip 95% of what I planned. Yeah. No, but I think it's good that you saw. So I really mean what I say. So in terms of positive embedding results, these two theorems, which are old, are really basic ways of looking at these problems. And there are the ways we look at, a lot of these understandings are are still the way we work today with metric spaces.
I have a question about the first
Mhm.
thing. So it seems that the proof relies on the chromatic number of this
Mhm.
CNet, so which could be presumably much less than the dimension. So is there a way of characterizing those metric spaces by the chromatic number?
Yeah. Yeah, you need a chromatic number at every scale.
Yeah. So you take the max, the sub.
So it's a good question. I haven't seen this done anywhere. But my hunch is that it's going to be very similar to.
These graphs contain big clicks, right?
Yeah.
Because you have all the net, all the part of the net that's inside
Yeah.
it's all a click, so the chromatic number is big.
Yeah, but I guess it's.
But it's not the same
if you
thing.
look at a grid in L1, it's not like I said. I mean, you really say,
No, you can relate the chromatic number in the click number, but.
It's not a good epsilon net. The grid is not the middle point of a grid in high dimension is very far from. This is not an net.
No, but what Bernard is suggesting is probably, suppose that for every scale, every net has a bounded chromatic number. In this, right?
I don't think this has been studied. Just my hunch is that it will not be very different, but it might be surprising.
So the question is there any metric space or symmetric that has that condition?
Then it's not double.
Maybe,
Is there a metric space like that? No, maybe it's doubling, but but it's not doubling.
perfect net. You can tie this.
I don't know. I don't think, I don't, to the best of my knowledge, nobody ever thought about it. It's a natural question.
Another unrelated question.
Yeah.
So, if you know that one metric space embeds into another metric space, and the mapping is one-to-one, then the second metric space also, the inverse is also an embedding, right? With the same
You mean the same size metric spaces? Currently I'm embedding an endpoint metric space into L2, so what do you mean? What you want to, so I don't understand the question.
To ask if you have an embedding
Of X into Y,
X into Y, that doesn't mean that Y also embeds under some conditions that Y should.
but X can have 4 points and Y can be infinite.
So I'm saying under some.
No, that was the cheating answer, but definitely no. So for example, so look at the function space L1 and look at the sequence space L1. So it's easy to show that this is isometric to a subset of that, but this does not embed by Lipschitz with any distortion into that. Okay, so these are space which but this is somehow really the worst possible example because they have exactly the same finite subsets.
So every second base is isometrically in L infinity, and L infinity doesn't.
Yeah, but these guys look almost the same. Okay, for every endpoint subset of capital L1 is an endpoint subset of little l1, isometrically. Okay, but still, this guy is in here, but this has no distortion at all. Okay, but this is a non-trivial fact. Okay, so. Okay, so what should we do? Let me not discuss more embedding theorems. I will show just the example of the application of what we did, Bourgain's theorem, to the sparsest cut problem, very quickly, and then those of you who are interested in more, I will give you references. Unless do you have does anybody want to hear specifically about how to prove that these log ends are optimal? Or that's one option. The other option is Johnson-Lindenstrauss, dimension reduction, or some application to computer science. I mean, so Noga decides.
Let's discuss it for 5 minutes.
No. You decide now. So let me explain the log and lower bound, because you smiled the most when I mentioned that.
He smiled because he's going to improve it.
because improve it. So here is the simplest way to see that this log n is optimal. So let G equals VE. So this is going to be, let's say, a bounded degree expander. So let's say a 3 regular. So by that I mean I look at the adjacency matrix. So Aij is a 1, 5J is an edge, 0 Ij is not an edge. And the second eigenvalue of A is less than 3 minus something, 0.001, doesn't matter. Okay? But the number of vertices is V. So this is just equivalent. So an equivalent formulation of spectral gap. So an equivalent formulation of spectral gap is the following. So let C be the smallest constant such that for every function f from the vertex set into the real line, the average of fx minus fy squared over all two vertices, that's at most constant times the average over edges. So an easy exercise in linear algebra, the smallest constant is precisely 1 minus 1 over the second eigenvalue. Okay, so that's just an exercise. Just expand it out and you see. Okay? But so first of all, whenever you have such an inequality, it immediately gets improved to a Euclidean inequality because I can just do this because I can do it for each coordinate at once, separately, and just sum up all the coordinates. Okay, because it was squares. So this is really the same thing. And now, so I want to bound C to G. G is going to be with the shortest path metric. So let's take the best, the function f. So if this is D, the function, the optimal embedding, the function f from G into L2, such that for every xy in G, the distance from fx to fy is at most d, the distance in the graph, and at least. So for this f, we can just look at the inequality, which is just a rewriting of the spectral gap, but we look at for the optimal embedding, and we can see. So what does star say? Well, the average over edges in E well, that's at most d squared because I use the Lipschitz condition, and on edges the distance is 1, and this is an average. Okay. On the other hand, the average over all pairs, because it's a bounded degree graph, it must be at least a constant fraction of the pairs, or must be at least distance log n apart, because this is bounded degree. So this is at least a constant times log n squared, and if you put the two things together, C is really a constant, you get that D is at least log n. Okay, so that is the reason. So it's good that I chose this because that was the shortest thing. I just want to say that I did a lot of injustice to, as I said, 95% of the theory. I ignored the issues like dimension reduction. I ignored issues such as other notions of embedding. You know, we just discussed by Lipschitz. There are all kinds of average versions and relaxed versions of embeddings which we really need in many situations. And I did very huge injustice to lower bound techniques. So metric inequalities of this form, even when you pass to other metric spaces, just in the case of expanders, you replace the norm 2 by another norm, or by other metric spaces, then you arrive at subtle questions which are open, and you know, even on expanders and are well-known, famous questions. And so these types of inequalities are subject of intensive study for, again, almost over 3 decades now. And so that's one direction, and the other direction is all kinds of other notions of embeddings, but I hope I gave you a taste of you know, the beginning of this theory. Any questions?